All right, the first thing we're going to do, we are now done with all the new material for the semester, which means for those of you who will only take Physics 213, you will never learn anything new about physics again. Yay. So, tomorrow is a tutorial. Who can tell me what I need is I need like 4 people to show up. If I don't get 4 to show up, we won't do it. Who in the room will be at the tutorial tomorrow in here at 1 o'clock? 1, 2, 3, 4, 5. Okay, we got enough. Next. Yes. Do the what? Oh, tutorial tomorrow will be about anything you want. So we can do, what we're going to do now is basically start answering whatever you guys want to know. 2 people have made suggestions about problem 14. Problem 14 is similar to the nightmare problem from Monday. Now what I'm going to do is do a few of the steps and then you guys really can do the rest on your own. In 14, in 14, we have a mass. In water, we have a string tied to the wall. This is a bar that can move up and down. Whereas on Monday, the problem was, given the third harmonic of x hertz, determine the volume of the object in the water. All we want is this tension. So in this particular case, we're going to work from the mass back to the tension rather than the frequency back to the mass. So in this part, the sums of the vertical forces is equal to 0. You have buoyant force up, tension up, mg down. You are given, you're given the mass. Ooh, that may be a decent idea. You do need the density. So I would say that it is, which obviously means we're not going to grade this if it's a couple hours before it's due. Set a density of 1,600 kilograms per cubic meter. We'll just do that on the fly. The density is mass divided by volume. So volume is mass divided by density. Now the mass of the object was given. So mg minus fb is equal to tension. M was given, gravity is known, fb is density of water, volume, gravity is equal to tension. Volume is mass over density. And this will be the density of the object. You now have everything that you need to get T sub h, which is the hanging tension. So you can get a number from that. The second part is a torque bar problem. You've got TH pulling down, you've got TY pulling up. TY is part of T, and there's TX, which we don't really use. For motion around here, we're only going to look at Ty and Th. Tx is directly at the rotation point, and Ty is the vertical component of T. Now the big difference is how the values are distributed. I gave you this distance, 1.5, and I'll call that x1. And then I gave you this distance, which now is x2. In the previous example on Monday, I labeled that as x2 and gave you that distance. And all you did was just take that and that to get the total. That's the rotation point. Sum of the torques is equal to 0. Ty x1, T hanging x2. To the right up positive, to the right down negative. And so we have our torque bar equation. Solve for Ty. Th x2 is equal to Ty x1, or Ty is Th x2 over x1. So now you can get a number for Ty. The last bit is to actually get T, and that is all trig. I give you that height Y, and then, let's do this. Theta is inverse tan of opposite Y over adjacent x1. Sine of theta is the opposite tension Ty divided by the total tension T. So T is equal to Ty over sine theta. And there we go. And that's it. That's how you get the tension. It's a 3-step. Now, really, if there was a 4th step, I would take that tension and then I would find the resonant frequency that string is vibrating at, and then you can do all sorts of things with that. But that's how it works. In this particular case, it's a light-duty hybrid problem where I have buoyant force, torque, and a little bit of trig tossed in. And that's 14. The rest is just plug and chug. I leave that to you. I know how much you love it. So who has another question? Or do we all understand all of physics? Which would be great. I'm using, I'm funny, ha-ha, like laughing at. Okay. At least you're on. Another buoyancy problem? Do you want, let's do a problem where you do have to concern yourself with the density of the gas inside. In fact, all right, what I'm going to do more paper, always helpful. And I brought my book. If no one's ever seen one, this is the book to the class. I know, almost no one has seen it. Air is 1.29 kilograms per cubic meter. The density of helium is 0.179 kilograms per cubic meter. I have a balloon. It's floating around in air, and actually it's just sitting there. No strings are tied to it, nothing. So it's doing nothing. If it's doing nothing, what do I know about it? It's what? The net forces are in the vertical are zero. It's not going up or down. I mean, we haven't even gotten to the question of the problem, and we're already coming up with information. The question is, if this thing is filled with helium and the mass of the shell is equal to 100 kilograms, what is the volume of the sphere? So the mass of the shell is 100 kilograms. I've got helium inside. The density of air and the density of helium are approximately the same. So you have to consider the fact that the helium inside the ball has mass. But we have the best information of all, that it's not doing anything. It's in translational equilibrium. The sum of the forces in the vertical are equal to zero. Well, what are those forces? Well, there is the force of the shell pulling down. There's the force of the mass of the helium times gravity pulling down. And then we have the buoyant force pulling up. Now, in this particular case, we're dealing with the surface of the balloon is infinitely flat. It's of infinite density. We're not taking into consideration the volume of displacement of the shell itself, just the totality of the sphere. So we have buoyant force, mass of helium times gravity minus the force of the shell is all equal to zero. Well, let's start asking questions. What is the typical expression for buoyant force? The density of the fluid it displaced, so density of air. The volume, well, we're looking for that, so we got to keep that letter in, and gravity. Now, the mass of the helium we don't have specifically, but we do understand that density is mass over volume. Mass is density times volume. So this is the density of helium times volume times gravity. The last part, the force of the shell. Force of the shell, mass of the shell times gravity. We have everything we want. We even have a G in every part, which means 0 equals rho A V minus rho H E V minus MS. We're going to look for V. I'm going to move the MS over. I'm going to factor out the V. MS rho A rho HE is equal to V. and that's the volume of the balloon. So the mass of the shell, 100, the mass of air, or density of air, excuse me, 1.29, the density of helium, 0.179. So the volume is 90 cubic meters, which is interesting because it's a good solid number. Okay, and so that's an example of a buoyancy problem where you do have to take into consideration of the the gas inside. Because there was a term of gravity in each one. So I divide, between this and this, I divided both sides by G. 0 divided by G is 0. All this divided by G, the G's just factor out or drop out. All right. So, do we have another, what's another request? Do what? No, it could be anything. What I'm trying to think of, I don't think that will be necessary for test 3. So I think, no, not any, okay, right now we're just covering test 3 related material. Final related material we'll talk about the week after next.
Do a frequency of a pipe or half pipe.
Okay. The what? Okay. Trying to think of something that. So you want. You have a pipe. Half pipe. The length is 2 meters. Oh, okay. I know exactly what we're gonna do. Okay, problem set 10, number 4. So you hear a train's whistle at 3,000 hertz as it comes at you and 2,400 as it moves away. Using only the 2 frequencies above, what is the velocity of the train? Classic Doppler shift problem. So you have frequency away for a moving source. That's an F. Frequency towards. If it's a moving source, the parentheses go in the denominator. If it's coming at you, you're going to hear a higher frequency, so the denominator must be less than 1. That's why a minus sign is there. If the frequency is heading away from you, you should hear a lower frequency. Therefore, the denominator must be greater than 1, so you have 1 plus. Now, I don't have the source frequency. In fact, this is a lot like, we were talking about this right after class on Tuesday. someone asked, like, well, what's a decent Doppler shift problem on a test? And I said, a year or two ago, no, it was like 2 years ago, someone asked for a Walking Dead themed test. And I was like, coming right up. So the question was, Daryl's driving his motorcycle and coming at you, you hear one frequency, moving away, you hear another frequency. What's the velocity of the motorcycle? This is the same thing. So what you do is you take towards and divide by away. You could do it the other way, it doesn't really matter. Towards is F over 1 minus V over Vs. Away is F over 1 plus V over Vs. This becomes 1 plus V over Vs, 1 minus V over Vs. This is the denominator of the denominator. That gets kicked up into numerator. That comes down, and so we're left with, and those cancel, obviously. So F towards over F away is equal 1 plus V over Vs, 1 minus V over Vs. Solve for V. Cross multiply. Distribute. Get all of your V over Vs terms on one side. Factor out the V over Vs. Solve for V. So now we use the number frequency towards 3000, frequency away 2400, away 3000, towards 2400, the base velocity 350. And I get a velocity of 38.89 meters per second. So that's the velocity of the train. Now, if it's using a whistle, what's the frequency of the whistle? Well, we now have the velocity, so you can use either one. We'll use towards. Towards is 3000, 1 minus V 38.89 over Vs, which is 350. And that gives me a frequency of 2666.7 hertz. And so that's the frequency of the whistle on the train. This frequency at that velocity coming at you would produce a frequency of 3,000 hertz. Now what's really interesting, the story behind writing a problem 4 is that it was initially like 6 problems, and I just took it and merged it into just one big problem. If the whistle on the train was a half pipe and the sound emitted was at its first overtone, what is the length of the whistle? So it's a half pipe. I want to know what length is. Emits a frequency. It's at its first overtone. What is the value of N for the first overtone? Interesting. You said 2. Now, what did we know about half pipes? They're only odd. So the harmonics go 1, 3, 5. The 1 harmonic is the fundamental frequency. The 3rd harmonic is the first overtone. The overtones don't care about the missing frequencies. All it cares about are the harmonics themselves. So the first time after the fundamental, that's the first overtone. It doesn't matter that N is 3. The frequencies are NV over 4L. So L is NV over 4F. N is 3, V is 350. That's 4, frequency 2666.7. Solve it, you got length. If the whistle on the train was a pipe opened at both ends and that the sound emitted was at its first harmonic, what is the length of the whistle? Well, for a whistle opened at both ends, the frequency is NV over 2L. N is 1 because we're dealing with the first harmonic. So L over V, or L equals V over 2F. V is 350. 2 times 2666.7, and there's your length for that one. If the whistle on the train wasn't a whistle but a guitar string of mass 20 grams and length 1.2 meters, convert the mass to kilograms. Actually, we'll use capital L since that's the typical term for length. If it was resonating at its fundamental frequency, what is the tension of the string? Okay, length 1.2. So the frequency for a string is NV over 2L. The velocity is the square root of tension over linear mass density lambda. Lambda is the mass of the string over the length. So taking these two, you could say that V is equal to tension times length divided by mass of the string. Substitute this into here. The goal is to find tension. Solve for tension. The first thing I do is square both sides. solve for t. And there you go. Now you're in plug and chug mode. L is 1.2. MS is 0.02. Frequency is 26667 square, or 0.7, square that. N is 1, so you can just drop that out. But, and there you go. Sure. So everything is squared and looks great, and there you go. Now really everything are just variants of strings, pipes, half pipes, the hanging mast at the end of a pole, and a vibrating string. I'll go over in that, or do we have any burning questions right now? Otherwise, I'll just go into something else. Okay. In that Walking Dead problem, there was a problem known as bucket of brains. And the class hated that problem. And I was like, what do you mean? And they were like, it's impossible. And I love hearing that's impossible being spoken by my students. Now, what I had done is I had set up a bucket, and the bucket had a mass. And inside the bucket were end brains. And because I understood that I think it would be bad taste to have actual pictures of Walking Dead zombies on the test. So for Walking Dead zombies, I replaced them with the zombies from Plants vs. Zombies to make it a little bit more lighthearted. So you had all these zombie brains in a bucket, and the mass of a zombie brain was, I said like 2 kilograms or something. So the question is, what's the number of brains in the bucket? How many brains do we have? Now, what I did is I set it up exactly like the ones before, X1, X2, and Y. And I said like third harmonic is equal to, has a frequency of 1800 hertz. And I said, let's say Y was 1, X1 is equal to 2, X2 is equal to 1. I wanted to know what are the number of, how many brains are in the bucket. And the way that I did this is, I'm gonna solve it alphabetically using alphabet soup. And then I'll plug in the numbers, and what we'll end up with is a fraction of a brain. So many brains plus some fraction. And what I did is I put it on a spreadsheet, and I put in an integer of brains, and I got it to work out so that it worked out perfectly. It was a beautifully constructed problem. Now, it's not a buoyancy problem, but it is a hybrid problem. You're dealing with torque bar and sound. The sound part comes from the string, NV over 2L. Now, L in this case is the square root of y squared plus x1 squared. And I'm going to keep it as L for a little while. I also had to give the mass of the string, let's say 20 grams. This becomes n over 2L square root tension over lambda solve for tension, F squared n squared over 4L squared T over lambda. So 4L squared lambda F over n squared is equal to T. Lambda is mass of the string divided by L. So this becomes 4L squared ms F over L n squared. The L's cancel, left with tension. So tension is 4L ms F over n squared. Now at this time, to keep our sanity, we'll plug in at the moment 4 1 squared plus 2 squared square root 0.02. I'm not going to have enough space. And there you go. Yeah. Why did I drop the square root of the previous? Of the frequency? Oh, wait. No, I didn't. So the tension is 64,399 newtons. I would probably think that something like, given a string at this frequency, that mass, and that dimension, give me the tension, that would be an acceptable appetizer problem. But to add this part in makes it more substantial. The torque bar is set up like this. F is the force of the branes. Ty is the tension in the y direction given by the plucked string. So that is theta, that is theta. Theta is inverse tan of y over x1. So tan inverse of y1, x1, 2. So theta is the inverse tan of 0.5. And I get 26.57 degrees. Ty divided by T is sine theta. So T equals Ty divided by sine theta. That makes it 64399 divided by sine of 26.56 degrees. Wait. Yes, because I was looking at this, and what I ended up with. Oh, what's T? Tension is the tension in the string that we got from plucking of the string. We need Ty for the torque bar. So Ty is T sine theta, or 64,399 times sine 26.56. And that gives me 28,795 newtons. How do I know I'm supposed to use sine? Because trigonometry demands it. Yeah. Okay. The bar is like this. The tension is like that. So there is a vertical component that we call Ty, and then there is a Tx. Add that to that, we get T. Now, the way that we do this is where the string is attached to the wall. We can get this theta. Theta inverse of y over x1. Theta is the inverse tan of y over x1. But this theta is also that theta. Two parallel lines bisected by a third line. You can say that that angle and that angle are the same. If that is t, and that's why I have the opposite side and I have the hypotenuse. Hence, I have to use sine theta. Yeah, that's because what I have there. If I needed to use Tx, I would use cosine theta is Tx over T. But I don't need anything to do with Tx. So I just use Ty and sine. Yeah, well, I would use inverse tan to get the angle, and then I would take the sine of it to work with T to get Ty. Torque bar problem. So in the torque bar problem, we have Ty x1, it's to the right up positive. We have FB to the right down in or negative. What? Where did I? Oh, the force, this is the force of the brains at the end of the pole. Well, what it is, okay, this is how I described it in the problem. You've got a bucket with a particular mass, and you have N brains in the bucket, each with a mass of 2 kilograms, or 3, whatever I put up on here. How many buckets how many brains are in the bucket? It's just, my worst review ever said, all Physics 213 is just word cloth. I'm like, yeah, that's what it is. So in the problem, that force of the bucket, or the force of the brains, is equal to the mass of the bucket plus the mass of the brains times gravity. The mass of the brains is equal to N times the mass of one brain. So this gives you the force down is mass of the bucket plus N times the mass of one brain times gravity. So this gives you Ty x1 minus mass of the bucket plus N mass of one brain times gravity is equal to 0. Now all I have to do is solve for mass of the brain. Ty x1 G mass of bucket minus G N mass of brain equals 0. Now all I have to do is solve for N. That's the task. Yes? Yes. Thank you. Thank you for paying attention. How am I going to fix this? All right. Yeah, they should be on both of these. So let me rewrite this. Ty x1 minus G mass of the bucket x1 plus x2 minus G N mass of the brain x1 plus x2 is equal to 0. Now I get to solve for N. So Ty x1 minus G MBU x1 plus x2 equals G N of mass of one brain x1 plus x2. So this is Ty x1 minus GM bucket x1 plus x2. And then GM BR x1 plus x2 is equal to N. And what I had here was, I had this equation, I plugged it into my spreadsheet, and I sat there and I played with it until I got a whole number to pop out, and the numbers worked perfectly. But really what we've been doing in this problem and the other problem is just algebraic manipulation. The setups of the problems are very similar. It's just, what variable am I looking for? And so that's the bucket of brains problem. Now thought I was about to share, but I'm not. So next question. A lot of this is kind of repetitive on problem set 10. If we can kill another like 10 minutes, then that would be enough for the day. Anybody else have a problem? Huh? You want me to plug the numbers in for that? Well, really, I mean, it's just plug and chug. Now, I promise that the N will not be an integer in this case, because I threw in numbers that were just bizarre. The way that I did it here is when I had the problem or the spreadsheet all set up, I plugged in the numbers so that N eventually became like 12. Like the number was not like 2 billion brains. It was a soft, like if you work through everything and you get the answer, oh, the answer's 12. Not like 12.02852112. I'm talking 12. Then that instilled a sense of confidence in the student. A roulette question? Well, the roulette question is the Doppler shift where you hear them coming and going, and that's it. No, you're not going to get a bar. You won't get a bar. I said, when I mentioned that the first time, I said there will be one time in a lecture where theta naught will run zero, but you will never have to do a problem on that one. So that's the problem. The Taro motorcycle problem is a legitimate problem. The setup, rather than, you could even do the problem where you're running very fast at a fixed source. You hear 1800 hertz as you head towards it, and you hear 1200 hertz as you go away. What was your velocity as you moved by the fixed target? You would do the same thing, but instead of using the moving source equations, you use the moving observer equations. So F towards is now F1 plus V over Vs. Frequency away is frequency 1 minus V over Vs. These cancel, and you just solve for V in the same way. Cross multiply, factor, distribute, all that stuff. It's the same procedure. And so the rest of it is just algebra. Problem set 1? 9? Oh, that. No. Problem with the earthquake one, you know what? I should end up making that a test 1 problem, because that's just motion. Don't spend any time studying that SP wave motion problem, because it was initially what I had done in the early years was I said we're going to do a thought experiment, and I said at this particular moment, because I was bringing them aware about the New Madrid fault line, that waves, earthquake waves, there are 2 types. There's a fast moving wave, which is one type, and then there's a slower wave. And what I did is, at this moment, we are experiencing the fast wave. 45 seconds later, we experience the slow wave. How far away is the earthquake? And it's a 2 equation, 2 unknown type problem. And we worked it out, and it's more of a motion problem. I should change the problem, edit it a bit. But there you go. It's so, bottom line, for the Mercenary 213 students in the room, I wouldn't bother with that problem. I don't even think I'm going to grade it. So it's a relic of a problem that happened a long time ago.
So, a moving observer
Yes.
source is
F over whatever their associated bracket. we're talking about 5. Problem 5 on problem set 9. Okay. So 5, to clarify, is this. We have another balloon. A 10 kilogram balloon is filled with helium. Its volume is 200 cubic meters. How much mass can it carry? I'll satisfy a particular question about the problem. The mass that you add to the balloon does not change any of the volumes that we're thinking about. Think about it as really dense paint. So you've got this balloon, it's 200 cubic meters. It weighs 10 kilograms. The balloon itself is filled with helium. How much paint can you paint on that balloon so that it remains neutrally buoyant? So you've got the balloon, you've got the buoyant force, you've got the force of the balloon and gravity pulling down. You've got the mass of the helium and gravity pulling down, and then you've got this additional force from the additional mass and gravity pulling down. So there are 3 quantities down. The mass of the helium, the mass of the balloon itself, this weird additional mass paint that you're putting on the balloon, and then buoyant force pulling up. You sum the forces in the vertical. It's neutrally buoyant, so the sum of the forces is 0, which is awesome. You have the buoyant force, mass of the helium, gravity, mass of the balloon, gravity, mass of the additional mass, and gravity. I'm looking for the additional mass. What is that? So additional mass, gravity, is equal to FB minus mHEg minus mass of the balloon times gravity, etc. Divide both sides by G. Additional mass, buoyant force divided by gravity minus the mass of the helium minus the mass of the balloon. The buoyant force is density of air, volume, gravity. The mass of the helium is density of helium times volume. Once again, density is mass over volume, so mass is density times volume. And then mass of the balloon. Now all you do is just plug the stuff in. Density of air, 1.29. V 300. Or I'm sorry, not 300, 200. Density of helium, 0.179 times 200 minus 10. And that will give you the additional mass. Shouldn't give you a negative number. Yes? The mass of the balloon, well, when you divided both sides by G, that G went away. Yeah. I could have done the step where I replaced FB with rho VG and then just drop them all out at the same time and whatever. What ends up happening happens. Yes. I will specifically tell you what is happening. Like, it will not be this. Or it will be one of those, like, it's rebellion gas. Find the density of the gas side. I'll have to get, and this is not biology. I do not expect you to memorize the density of all these different materials. That's not important. How you manipulate the equations are. Any last questions? All right. Tomorrow, 1 o'clock, answer anything you guys want to do, and enjoy a good baseball game tomorrow.